In the previous lecture, we discussed about the wave propagation in a transmission line and particularly focused on the characteristics of lossless line. In this lecture, we discuss about the lossy transmission line. We discuss about a special form of lossy line which is called distortionless line, and we also discuss the terminated lossy lines. So, we have already seen that for a transmission line, the complex propagation constant is given by gamma is equal to alpha plus j beta. Here this component alpha actually attenuates the wave as it propagates, and beta is the phase constant. So, that is why we call alpha as the attenuation constant and beta as the phase constant. Now, if we square this equation on both sides, we can write alpha plus j beta square is equal to r plus j omega L into g plus j omega c. Now, if we expand these equations and write both the left and right hand side in the form of real and imaginary parts, and then if we equate these real and imaginary parts, we get alpha square minus beta square is equal to R g minus omega square L c, and 2 alpha beta is equal to omega L g plus R omega c. So, this is the real and imaginary part separated, and once we have this form, we have two unknowns alpha and beta to be calculated in terms of the line parameters, that means R, G, L and C, and also frequency omega. So, if we solve these equations, we get the solutions for alpha and beta, and these are the general solution for alpha and beta in a lossy line. Now, what happens in practical cases? The transmission line losses are usually small, and when we are using short section of transmission line, essentially the signal attenuation will not be much, and some approximation can be made to simplify the expression for the parameters gamma and z naught for the case of low loss line. So, we can rewrite the propagation constant in this form, and which can be rewritten in the form shown, where we have j omega under root L c that is taken out, and we have written in the form r by omega L, g by omega c. For the low loss case, we assume that at the operating frequency r is very small compared to omega L, and g is very small compared to omega c, and therefore, this product term R g by omega square L c will be even smaller, and as compared to 1, it can be neglected. Then once we neglect this term, and for the remaining term we apply Taylor series approximation and retain only the significant terms, then we can write gamma, the propagation constant, approximately j omega root L c into 1 minus j by 2 r by omega L plus g by omega c. So, now what we can do? We can find out the real and imaginary parts of this equation, and from there we find that alpha is half r root c by L plus g root L by c, and beta is omega root L c. So, if we look at the expression for alpha and beta, we find that attenuation constant alpha now does not depend upon omega, it depends only on the transmission line parameters, and the phase constant beta varies linearly with omega, and characteristic impedance Z0 for such line can also be found out, and we write Z0 is equal to root L by C r by j omega L plus 1 g by j omega c plus 1, and this r by j omega L with respect to 1 will be very small. Similarly, g by j omega c, that term also will be very small compared to 1, and Z0 can be approximated as root L by c. Now, we come to a very special case of transmission line, which is known as distortionless line. So, we have seen in general alpha and beta for a transmission line are complicated function of omega, the angular frequency. When alpha varies with omega, different frequency components of a signal, if it is present, will get attenuated to different extent. Similarly, if beta is not a linear function of omega, that is of this form beta is equal to some a omega, the phase velocity V p, which is given by omega by beta, of the individual frequency components will vary, giving rise to dispersion. So, we find that if alpha is varying with omega and beta is not a linear function of omega, in that case both the attenuation and the phase velocity for different frequency component will be different. However, a special condition exists for a lossy line that can have attenuation constant independent of frequency and phase constant varying with omega linearly. And this type of lines, if we can realize, they will not distort the signal, and therefore, this type of lines are called distortionless line. So, let us assume that the transmission line parameters we have designed in such a way that they satisfy the condition R by L is equal to G by C. So, we have designed the transmission line to satisfy this requirement. In that case, we once again write gamma, the propagation constant, in this form, where we have the terms R by omega L and G by omega C. Then, since R by L is G by C, we can club these two terms and we get 1 minus j R by omega L whole square, and therefore, gamma expression now simplifies to j omega root L C 1 minus j r by omega L. So, if we compute the alpha and beta, the real and imaginary part of gamma, we get alpha to be equal to r c by L and beta equal to omega root L c. So, we find that beta is now varies linearly with omega and alpha does not contain any omega term. So, this is a specific condition in a transmission line, and if this condition can be achieved, then there won't be any distortion of the signal. Please note that although we are considering in terms of a single frequency omega, when a signal is transmitted, this signal will have multiple frequency, more than one frequencies, practical signal, which are used for communication. And if this condition is satisfied, then all frequency components of that signal will be attenuated, their strength will be reduced, but they will be attenuated equally. Similarly, the phase shift beta, being a linear function of omega, will result into phase velocity which is same for all the frequency components of the signal. So, the signal waveform will not get distorted, and that is why we call this type of transmission line having this property of R by L is equal to G by C as distortionless line. With this condition, R by L is equal to G by C satisfied, let us see what happens to the characteristic impedance Z0 of the line. The characteristic impedance Z0 is defined as square root of R plus j omega L divided by G plus j omega C. Now, we can write this expression into the form shown, where we find that in the numerator under the root R by omega L is same as G by omega C in the denominator, and these two terms will get cancelled. Finally, we will get Z0 equal to root L by C, and characteristic impedance becomes real and its value is same as that of the lossless line. So, this is an interesting property of the characteristic impedance of the distortionless line. So, let us now consider another case when a transmission line having a propagation constant gamma and characteristic impedance Z0 is terminated to a load impedance ZL. We set the reference distance Z is equal to 0 on the load itself, and we see what happens at a distance Z is equal to minus L. So, the expression for voltage and current wave on this lossy line can be given as here gamma is the reflection coefficient at the load, and we have seen that gamma is equal to ZL minus Z0 divided by ZL plus Z0. Now, if we are interested to know the reflection coefficient at a distance L from the load going towards the negative Z direction, then we can write gamma L is equal to gamma, the load reflection coefficient, multiplied by e to the power minus 2 gamma L, and this can be written in this form, and therefore, the mod gamma L will be mod gamma e to the power minus 2 alpha L. We can compute the input impedance of a lossy transmission line as follows. We consider a distance L from the load, and we can write Z in to be equal to V Z is equal to minus L divided by I at Z is equal to minus L, and then we substitute the equations for the voltage and current, and then replacing the reflection coefficient gamma expression by ZL minus Z0 divided by ZL plus Z0, and reorganizing the terms, we get in this form. And finally, we find that the input impedance expression comes in terms of hyperbolic functions, and from this stage, if we divide by 2 cos hyperbolic gamma L, we get a more compact form of the input impedance of a lossy transmission line, which is given by Z in is equal to Z naught ZL plus JZ naught 10 hyperbolic gamma L divided by Z naught plus JZL 10 hyperbolic gamma L. Please note that when alpha equal to 0, then this 10 hyperbolic gamma L will be 10 hyperbolic J beta L, and which can be finally written as J of 10 beta L. From this expression, we will get the expression for the input impedance of the line that we derived for the lossless case. Let us now consider the power in a terminated lossy line. The power that is delivered to the input of the terminated line at the position Z is equal to minus L can be written as P in equal to half real part of V at Z is equal to minus L into complex conjugate of the current at Z is equal to minus L. And when we substitute once again the expression for the voltage and the current, then we can get and only retain the real part. We get the expression for the input power at Z is equal to minus L, and this has been written in this particular form. Now, if we use our earlier relation of mod of gamma is gamma L is equal to mod of gamma e to the power minus 2 alpha L, then we can represent here. Please note, in the previous equation the power is in terms of reflection coefficient gamma at the load, whereas in this expression the power is in terms of the reflection coefficient at z is equal to minus L. So, once we get the input power, we proceed to calculate the power that is delivered to the load. This is given by half real part of V at z is equal to 0 complex multiplied by complex conjugate of current at z is equal to 0, and we can write this is V naught plus magnitude square divided by 2 z naught 1 minus gamma square, where the gamma is the load reflection coefficient. The difference in the power corresponds to the power lost in the line. Please note that in lossless case we have power only delivered at the load, but in case of lossy transmission line, as the wave propagates, because of this attenuation factor alpha, some power will be dissipated throughout the line, and whatever power we compute at z is equal to minus L and the power that we compute at the load position. So, if we take the difference of these two power, that will be giving us the power lost in the line. So, P loss is P in expression which we have already computed minus P L, and this can be found out by substituting the expressions for P in and P L. And after rearranging these terms, we can write the P loss into two components. The first component, it gives the power lost by the incident wave, and the second component is the power lost by the reflected wave. So, in a transmission line, we will have both the waves present, and both incident and the reflected wave, because of the attenuation in the line, will lose power, and these two expressions account for the power lost by the incident and reflected component of the wave. P L is the load power which is finally delivered, and P loss is the total power loss because of the incident and reflected wave. So, this brings us to the end of our discussion about the lossy line. In the next lecture, we are going to cover what is known as Smith chart, the basics of Smith chart. Smith chart is a widely used graphical tool for solving transmission line problems, and in the next class we will discuss about the Smith chart.